Okay, 7.2, velocity. So let's recall. Velocity has both a direction and magnitude, okay, and therefore it's a vector. Two vectors can be combined to determine their resultant velocity, with the resultant of two velocities being their sum. Okay, so example 1. An airplane has a velocity of vector v relative to the air when it encounters a wind having a velocity of vector w relative to the ground. Draw a diagram showing the possible positions of the velocities and another diagram showing the resultant velocity. Okay, so just please note, when dealing with velocity of airplanes, we consider the velocity of the airplane relative to the ground. And what that means is, like, if you were standing on the ground and you were viewing it from down here, which isn't quote unquote moving, right? Even though the earth is moving, but we do it relative to the ground as like the stable position. Okay, so say for example, the airplane is traveling east and that'd be vector v. Then some wind is going to come and it's going to push it, and that's going to be vector w. But we know that we can't go head to head, so we're going to, you know what, let's pick this one up and we're going to relocate it. So vector v is going to look like this still, but then vector w is going to be here. So now it's head to tail. And then we're going to get some resultant. Okay, this could have been any sort of situation. So the airplane could have been going north, and then, okay, the airplane could have been going north and then encountered maybe a wind from this direction. So this would be vector v, vector w, and then our resultant vector would be looking like this, right? Vector v plus vector w. Okay, so lots, like unlimited ways to draw this. Example 2. A plane is heading due north with an airspeed of 400 kilometers per hour. Okay, when it's blown off course by a wind of 100 kilometers per hour from the northeast. So I'm thinking, okay, so we've never eat shredded wheat. Our plane is going north, so our plane is going this way, and we're having a wind from the northeast. So when we talk about northeast, we're specifically talking about 45 degrees. Okay, so it would be like north 45 degrees east, or it would have a true bearing of just 0.45 degrees. Okay, the thing is, it's coming from the northeast. So if we were to draw this, we would draw 400 kilometers per hour, and then we'd have the wind coming from the northeast, so this being 45, this also being 45, and that one would be 100 kilometers per hour. Okay, this is called the position diagram. Okay, this is that tip-to-tip diagram. And what we want to do is we want to relocate maybe this 100 kilometers per hour vector so that we can do it tip-to-tail. So let's draw it down here. Yeah, so I'm going to go 400 kilometers per hour. Okay, north, and then I'm going to draw this one, 100 kilometers per hour from the northeast. Okay, so from the northeast means that we're actually going southwest, going in that direction. Okay, and then the resultant is going to be this right here. So let's call that vector R. Okay, and I'm going to label this one vector diagram. Okay, and just for simplicity, let's label this A, B, C. So if we're looking at the magnitude of the resultant, so magnitude of the resultant is going to use cosine law. Okay, so if we think about this, we think about this being 45 degrees, that means in here, this is also 45 degrees, right? Because those two are complementary, so they have to add up to 90 degrees. So vector r squared is going to equal, which is c squared, that's fine. Okay, let's name this vector a squared plus, we'll name this one vector b, the magnitude of vector b squared minus 2 times the magnitude of vector a times the magnitude of vector b cos theta, or we can say cos c. Okay, so the magnitude of that resultant is going to be vector a, 400 squared plus 100 squared minus 2 times 400 times 100 cos 45. Okay, so if you have a good calculator, you can put this entire formula into your calculator. So we have 400 squared plus 100 squared minus 2 times 400 times 100 times cos of 45. Okay, 45 is degrees. Make sure you're in degree mode. So I get 113,431 and then a bunch of decimals. Okay, so the magnitude of vector r, which is the resultant, is going to be the square root of this number, and I get 336.8. So let's just round 337. So going back to the original question, it asks, determine the resultant ground velocity of the airplane. So therefore, the resultant ground velocity is 337, and that's going to be in kilometers per hour. Okay, so let's label this R 337. Okay, so now we have all three sides, and what we want to do is we want to find this angle here so that we can tell the direction that our resultant vector is going. Okay, so we have 400, 100, and then we're gonna find the angle that's opposite the 100. Okay, so and then 100 is the B. So that's going to look the same. So we're going to have magnitude of vector b squared equals magnitude of vector a squared plus magnitude of vector r squared minus 2 times the magnitude of vector a times the magnitude of vector r cos b. Okay, the b is what we're going to be solving for. So if we're subbing in b, a, and then r, b is 100, a is 400, r is 337. So we get 100 squared equals 400 squared plus 337 squared minus 2 times 400 times 337 cos b. Okay, so I'm going to do 100 squared, and then I'm going to bring over, so minus 400 squared, and then we're going to go minus 337 squared. Okay, and I'm going to put that all in my calculator at once. Then I'm going to multiply negative 2 times 400 times 337. And then I'm going to leave that on that side. So 100 squared minus 400 squared minus 337 squared. I get negative 263,569. Okay, and then on this side, I get 269,600 cos b. Oh, that's negative. So I'm going to go ahead and divide both sides by negative 269,600. Okay, those cancel out, and I get negative 263,569 divided by negative 269,600, 0.9776298, and so on. Okay, that's clearly not our angle. We've solved for cos b, So what we want to do is we want to inverse both sides. So let's go ahead and inverse this side, and we're going to get angle B is 12 degrees. Okay, so angle B is 12 degrees. So going back to this diagram, we got 12 degrees in here. So what this means is the resultant is going 337 kilometers per hour, north 12 degrees west. Okay, because we're starting from north and we're rotating 12 degrees toward the west. Example 3, a river is 2 kilometers wide and flows 6 kilometers per hour. Anna is driving a motorboat, which has a speed of 20 kilometers per hour in still water. And she heads out from one bank in a direction perpendicular to the current. A marina lies directly across the river from the starting point on the opposite bank. Okay, so let's draw this situation right now. So we have some river that's 2 kilometers wide. Okay. And if we think about it, the river is like kind of going down like that. Okay. So the river is flowing in such a way. So either up or down. Okay. So let's go 6 kilometers per hour. The river is flowing. Now Anna is driving a motorboat. So maybe Anna is on this side of the riverbank, and she's driving a motorboat at 20 kilometers per hour. And right across from Anna, there's a marina. Let's call that M. So M is the marina, A is for Anna. Okay, so the question is, the first one, how far downstream from the marina will the current push the boat? Okay, so just a reminder, this here is called the position diagram. This is just a straight diagram of what's going on. Okay, these are usually made tip to tip. Now we're going to rearrange this, okay, and we're going to draw the vector diagram for speed. Okay, so if we think about it, Anna's here, we're going 20 kilometers per hour. The marina's here, she's getting pushed downstream at 6 kilometers per hour. So this is actually where Anna is going, the resultant. This here is called the vector diagram. Okay, and just to note, everything in this diagram is considered in speed. So A, how far downstream from the marina will the current push the boat? So what we have to do is we have to make another diagram for the distance. Okay, so we know that this is going to be 2 kilometers. We don't know the distance that she's going to be pushed downstream, so we'll leave that as X. And this is going to be the resultant. Okay, so this, again, vector diagram, but this time this is for distance. Okay, so let's call this A, M, B, and let's call this C, D, E. So a little bit of a different approach. We can use similar triangles. Okay, so if you remember from grade 10, triangle AMB in that order. Okay, so we have to do relative to the angles. Is going to be equivalent or similar to CDE. One of these diagrams is in speed, kilometers per hour. One of these diagrams is in distance, which is just kilometers. So what we can do for the similar triangles is we can say A. Okay, so side AM is similar to side CD. So those two sides are going to have their same ratio as side MB and side DE. So we're trying to find DE. We're trying to find this X value. And we have a full ratio, AM, which is 20, over CD, which is 2. And then we have BM, which is 6. So let's cross multiply. We get 20x equals 12. And then we're going to divide both sides by 20. And we get x equals 0.6. Okay, because it's here, it's going to be 0.6 kilometers. Okay, so we can just say, therefore, the boat will travel 0.6 kilometers downstream from the marina. Okay, so B, how long will it take for the boat to cross the river? So first what we want to do is we want to find the resultant number of kilometers. Okay, so what we want to do is okay, so we're going to try to find vector CE. Okay, so the magnitude of vector CE squared is going to equal, and this is just Pythagorean's theorem, the magnitude of vector CD squared plus the magnitude of vector DE squared. Okay, so this magnitude is going to be 2 squared plus 0.6 squared. Okay, so the magnitude of vector CE is going to be 2 plus 0.36, which is 2.36. And then when we square root it, I'm going to keep the same number of decimals. I'm going to go 1.54. Okay, so 2 squared is 4 plus 0.6 squared, which is 0.36. So we get a total of 4.36, and let's go ahead and square root it. And we get 2.1. Okay, so the magnitude of vector CE, which is the resultant vector, is 2.1 kilometers. So if this is 2.1, let's use similar triangles again to solve for this vector R. Let's call this R1. This can be R2. Okay, so we're going to still do the AM over CD. But then this time it's going to be vector R1 over vector R2. So we're going to have the same 20 over 2 equals R1 over 2.1. And this time it's a little bit easier because our R1 is already in the numerator, so we can just cross multiply. 20 times 2.1 I get 42 over 2 equals R1, and then divided by 2, I get 21 equals R1. Okay, so coming back to here, this is going to be 21 kilometers per hour. So let's go back up to the question. What is the question asking us again? How long will it take for the boat to cross the river? Okay, so if the boat is traveling at 21 kilometers per hour and it needs to travel 2.1 kilometers, all we want to do is we want to divide 2.1 divided by 20.1, and we get 0.1 hours. Okay, 0.1 hours doesn't really mean much. We want to then take 0.1 and multiply it by 60. Okay, because hours has 60 minutes in it. And we get 6 minutes. So we can say, therefore, the boat will take, or Anne will take 6 minutes to cross to the other side. Anna. Sorry. This is divided by 21. And then we get 0.1. So C, if Anna decides that she wants to end up directly across the river at the marina, in what direction should she head? Okay, so we're trying to find the direction. And what is the resultant velocity of the boat? Okay, so this one's a little bit different. So we originally were thinking, okay, if she heads across and then the stream pushes her down, she's going to end up like 600 meters or 0.6 kilometers down from the marina. Well, her goal now is she wants to head out in a certain way here, right? So she wants this to be her resultant so that, let's call this W, okay? The stream is going to push her down 6 kilometers per hour. And she's actually traveling at, sorry, this is vector V, okay? Because this is how she's actually going, okay? So she's actually going at 20 kilometers per hour. So she can just angle herself. She doesn't have to go, like if we're thinking never eat shredded wheat, she doesn't have to go east. She can go at an angle. She's still going to be traveling 20 kilometers per hour. Okay, so sorry, then we want the resultant to be whatever she's traveling plus that angle plus whatever she's getting pushed down, and we want that to be completely straight across at M. So let's call this A, M, and let's just call this B. Okay, so if we were to think about this, we can solve for the velocity of the velocity of the resultant, which is Pythagorean's theorem. And we can solve for this angle. So what angle should she set out at? We can solve this just by SOHCAHTOA. Okay, so let's do SOHCAHTOA first. Okay, we have opposite, which is 6, and we have hypotenuse, which is 20. So we're going to use sine. So sine theta equals opposite over hypotenuse, which is 6 over 20. So I get sine theta equals 0.3. And when we sine inverse both sides, I get theta equals 17.5 degrees. Okay, so this is 17.5. And now, if we have vector W and vector V, and we want to find the resultant vector, okay, we're going to have vector W, the resultant, squared, plus the resultant of V plus W, vector V plus vector W squared, equals vector V, magnitude of vector V squared. So we're going to have 6 squared plus the magnitude of vector V plus vector W squared equals 20 squared. Okay, I'm going to simply bring this one over, and we're going to get, and if you want to rename this R, that's fine. Okay, but we're going to get the square root of 20 squared minus 6 squared, which is going to be 400 minus 36. Which is going to be 364. And when we root it, we get 19. Okay, so this right here is 19 kilometers per hour. So, therefore, if Anna wants to cross directly she must depart at an angle of 17.5 degrees upstream. You know, that's assuming that the current is going downstream. That makes sense. Okay, while her boat will be traveling at 19 kilometers per hour. Okay. So even though she's going 20, because she's getting pushed at a rate of 6 kilometers per hour in a different direction, it actually slows her down.